pleasure to have Paramita visit us again. I think she said her last visit was in 2019 when she was still at Uppsala. She did her PhD from Sama Institute, and then she worked with Jainahar and Arijit at IOP, and then moved to Uppsala University, where part of the work she'll be presenting is today is has been carried out. And I think last year you returned to India and joined Vitstilani first, and then now you're at PRO. So she'll be talking to us about Bogolubov Fermi surface and exotic group of pairs and J equal to 3 by 2.
Thanks for the introduction. And also, is it fine for who are those who are attending online? Can they hear me?
Can you hear her online?
Yes. Yes.
Oh, okay, fine. Yeah, thanks. Thanks, Professor Maudhu, for the introduction and also yeah. And also, I'd like to thank Dr. Basu and Professor Maudhavan for hosting my visit and welcome you all. Okay, so today I will be talking about this Bogolubov Fermi surface and the exotic Cooper pairs in particular type of superconductor. This is different from conventional BCS superconductors. So this is a particular type of Fermi surface. It's a topologically protected Fermi surface, very recently found in some this type of superconductors and also different other superconductors, but not ordinary superconductors. So I will start. So I will at first start with some introduction to superconductivity, and then I will describe what is Bogolubov Fermi surface and how to detect that, where can we find that. So these things I will be talking about in this part, and then I will look for the connection between the Bogolubov Fermi surface and the exotic pairings that can be found in this J by equal to 3 by 2 superconductors. And mostly we have found some motivations that we can find some odd frequency pairing there, and this Bogolubov Fermi surface are related. This is related to this odd frequency pairing. So I need to define odd frequency pairing at first, and that I will define for spin half systems at first. Then I will move to spin 3 by 2 systems, where I will find out what are the possible pair symmetries, and then I will identify those odd frequency pairing. Finally, I will connect the odd frequency pairing to the Bogolubov Fermi surface, and then I will end up with the take-home message. Okay, so let us start with the introduction to superconductivity. So as we know that, so superconductor is particularly a material where we can see the current can flow without any resistance. So that is a zero resistance state. And it was first discovered by Kamerlingh Onnes in 1911, where he found the transition temperatures around 4.2 Kelvin. And later people are looking for the high TC superconductors as TC as high as possible. But this is not the sufficient description for definition of a superconductor. A superconductor can also, it shows Meissner effect. So it expels all the magnetic flux lines. So if I apply a magnetic field across say a normal metal ball, and so this blue ball, and then if I apply a magnetic field, then all the magnetic flux lines will pass through the material. Now, if you cool down the system temperature and then finally if we arrive the temperature less than transition temperature, that means in the superconducting state it will expel all the magnetic flux lines. So this is the so-called magnetic Meissner effect. So, but I am not going into much detail of all these things. So this is just the definition of a superconductor. So superconductor will show the zero resistances and also the Meissner effect. Now the question that I started with, that is the Bogolubov Fermi surface and the connection to the Bogolubov Fermi surface to the odd frequency pairing. So before I describe what is Bogolubov Fermi surface, or to describe that, I have to start with the basic density of state for ordinary BCS superconductor. And BCS superconductor, we know that there is a gap in the density of state. So, but if I go to the momentum space, this is the density of state I am showing as a function of energy. Now, if I go to the momentum space picture, so this is the normal state Fermi surface. So the three directions we have is kx, ky, and kz. And in the superconducting state, it is gapped and gapped in all directions. So it's full gap structure in the BCS. Now it is possible to find some nodal lines across which this gap can vanish. So those are called nodal lines. And these line nodes are possible to find mostly in the wave type of superconductors. Now, not only line nodes, it's also possible to find some point node. So exactly at some points, the gap will vanish. So at these 2 points, particularly. So this can be found in D plus ID type of superconductors, and those are completely different from ordinary S-pair spin single BCS superconductors. Now, recently it has been found that apart from these line nodes and point nodes, there can be another structure for the where gap will vanish. So that means this line nodes can inflate into a finite width region. So those we call the Bogoliubov Fermi surface, because it is a Fermi surface. It encodes the Bogoliubov quasi-particles. So across this region, this gap will vanish. And not only this type of ring-like structure, we can also some inflated point type of regions. So those are Bogoliubov Fermi surface. The important or interesting thing is that, so it's topologically protected. So it's different from this type of nodes or point nodes what we have found previously. So where can we find this Bogoliubov Fermi surface? So as I mentioned, it's topologically protected. So that means there should be some underlying symmetry which can protect this Bogoliubov Fermi surface in this type of superconductors. So I will come back to this question that where can we find or in which kind of superconductors we can find this Bogoliubov Fermi surface. I will come back to this point later. So Bogoliubov Fermi surface is a topologically protected region of zero energy excitations in a superconductor. So as I have shown this orange-like regions. Now its dimension is equal to that of the underlying normal state Fermi surface. It is different from the completely different from conventional BCS superconductors, where we can only find this fully gapped structure. It's also different from the unconventional superconductors, which can host these line nodes or point nodes. Now, another difference is that in this case of line node or point node, the dimension is less than that of underlying Fermi surface, but here the dimension is the same as the underlying Fermi surface. Now, where to find this? In which kind of materials or systems we can find this Bogoliubov Fermi surface? I will come back to this question after 2 slides, but before that, I want to just talk about the detection of Bogoliubov Fermi surface. How to detect that? We are hopeful for some upcoming experiments. A few people or a few groups are trying this kind of experiments to detect Bogoliubov Fermi surface. But till now, there is no result or published result for the detection. So it's very recently found actually the properties of some unconventional superconductors. But there are some predictions, some theoretical predictions that we can have a look at the spin polarized spectral function. That is but basically via the RPS measurements, where you can detect the finite width Bogoliubov on the surface. Particularly in this paper, they have described that possible detection. We are also working on possible detection. Hopefully, we'll come with some good results. Okay, so one can look at the specific heat and differential conductances. So basically the zero temperature specific heat or the zero frequency tunneling density of states. Also there is possible to look at the superfluid density. And they have predicted that it is possible to find the positive stiffness for these Bogoliubov Fermi surface superconductors. But the point is that still now the explanation is not rigid. We do not know that why Bogoliubov Fermi surface should give this positive stiffness. No one knows actually till now. But it's a prediction that people can get a positive stiffness. So more works to be need to be done in this direction to. And one can also find the finite or see the finite band, finite width in the energy band. So that is also possible because in general, so ordinary superconductors, we cannot get this kind of finite width, also finite bandwidth because of the full gap structure. And also for line nodes, you can have maximum a node, but here we can have some finite width regions. So those are the differences from ordinary superconductors that we can utilize to detect the Bogoliubov Fermi surface. Now let us come back.
So you are saying that initial definition is now you are saying that you have to have the nodal lines where the gap is. What is the mechanism for that?
Yeah. So till now there are different. At first, we need to know that which kind of superconductors we can find it. So till now there are some predictions. So it depends on what kind of underlying symmetry that we have. Mechanism for this kind of superconductors we do not know right now. So particularly we are also we in this work in this presentation I will also discuss the possible pair symmetries in particular type of superconductors where the electrons are this J total angular momentum quantum number 3/2, but we also do not know the mechanism till now. But one group tried to explain it as in a main by taking the main field description what we do for ordinary BCS superconductors. So that worked, but we cannot say that that is perfectly describing. We actually do not know. Right?
BCS like this Bismuth selenide or dope Bismuth selenide. Those
Yes.
superconductivity.
Yeah,
But
there is
those
a
are
yeah.
not those are not nodal lines, but they have some topologically protected states.
Yes, but here till now the pressure thing no one has checked.
Yeah, I mean.
Yeah, that I understand. Yeah. So what people tried that so using the same explanation of BCS, try to get the information as much as possible. But till now no one knows. Actually, that is not the perfect description, of course. So we do not know actually. We need to find out. So the people, so till now, the people who were trying to explore this Bolivar Fermi surface, they tried different pair symmetries. Actually, we also don't know which kind of pair symmetry is suitable for this Bolivar Fermi surface. So people are working on that area at first. So once we understand or get the total picture, then we can try to how to describe this one because the ordinary business theory will not work. But that we need to know the pair symmetry because BCS we knew that there's a spin singlet state inside a state, but here we don't know which. So there are different predictions for that. So we are actually worked on the little bit on the same line, but little bit different also. So we also tried to explain the connection because this kind of superconductors can hold what kind of symmetries that we try to look at. So once we know that all the possible pair symmetries, then we can try to explain. Actually, we don't know. No one knows. Yeah. Okay, so where to find this Bogoliubov Fermi surface? So I mentioned previously that it's a topologically protected region. So one should have some topological underlying symmetry in superconductors which can host this Bogoliubov Fermi surface. So superconductors which preserve the charge conjugation and parity but break time reversal symmetry can show this Bogoliubov Fermi surface. The non-centrosymmetric type of superconductors, which does not have any kind of or any inversion symmetry and broken time reversal symmetry in the superconducting state also, and this symmetry is broken in normal state. So this type of non-centrosymmetric superconductors can also host this Bogoliubov Fermi surface. Materials with particular like AGTE with the time reversal symmetry and the cubic symmetries with S and P type orbital where the total angular momentum is 3/2 that can also show this value on the surface with J equal to 3/2 but D orbitals with strong Coulomb interaction and spin orbit interaction, and this example is pyrochloroiridates. There is only one work in this direction or in this particular type of materials. And J equals to 3/2 states which has plus p orbitals like half-Fusler type of materials. And half-Fusler type of the composition is X, Y, Z, where X and Y are transition metals and Z is a p block element. And this type of material can, here all the electrons will have this J equals to 3/2 states, and this basically has this strong spin orbit coupling that breaks the inversion symmetry but preserves the time reversal symmetry. So one thing here you have to notice that so always there is some underlying symmetry which can protect the Bogoliubov Fermi surface topologically. Okay, so these are some predictions till now. So all these kind of systems can host Bogoliubov Fermi surface, but I will focus only this material, this half crucial type of materials, where we can have this J equals to 3 by 2 states with strong spin orbit in presence of strong spin orbit coupling. Okay, so why or how can we get these J equal to 3 by 2 structures that I can describe a bit here. So this is a normal state band structure. So we will have this conduction band that is S-like and the P-like valence band. Now once we consider this strong spin orbit coupling that breaks the inversion symmetry, so we can have some band inversion which is very similar to what we find in topological insulator. So this band inversion can give rise to a topological phase. This is basically a topological semi-metal where the valence and the conduction band they touch each other at these certain points. So here all the electrons will have S, that is spin quantum number half, and P-like orbitals. So L equals, that is L quantum number equals to 1. So the total angular momentum quantum number will be 3 by 2. So electrons will have the effective spin. So this J equals to 3 by 2. This is not the actual spin, it's actually the total angular momentum. So strong spin orbit coupling that leads to the band inversion, similar to what we find this topological insulator. Interestingly, not only these band touching things, we can also have some this kind of Fermi surface that encodes the J equals to 3 by 2 electrons. That means it is possible to find some pairings, possible to find some Cooper pairs where both the electrons both the electrons have J equals to 3 by 2. Now, in some experiment, it has been shown that this kind of material can show superconducting ground state. And that is why we are interested in this material. And not only superconducting ground state, it can show some unusual properties. That means the low TC, which is different. Low TC is not sufficient actually. So better to say this lower upper critical free, low penetration depth, and very similar to the non-centrosymmetric superconductors, but very low carrier density. And this is the difference. Actually, in BCA superconductor, we usually have this carrier density is very high. But here, the carrier density is very low, still it shows the superconducting ground state. And that is the interesting thing in this type of superconductors. So it's different from ordinary BCA superconductors, and at the same time, it's different from non-centrosymmetric type of superconductors. So it's completely different. We don't know actually how to describe or how to what is the possible theory to describe all the properties of this kind of superconductors. So this is exotic superconductivity. So it is so we can find it's possible to find some exotic pairings too. So what are those possible super pairs that we are asking?
So your Fermi level need not be at your band inversion point or
No,
far away.
no. Actually, it's possible to find it will be here or here.
And even then you have.
We need actually for superconductivity, we need a possible Fermi surface first, and that Fermi surface is actually it encodes.
Band inversion leads to how would that also contribute to topological property? Because it's
Yes.
far away from
Once we get this this band inversion, that means we are in the topological phase, and that is whatever the Bogoliubov Fermi surface we are getting in the system. So that is topologically protected.
Now the question is because so it doesn't have to be at the Fermi level, the band inversion. I mean the band inversion.
No, because here generally people little bit dope it. Generally people dope it, so it's need not to be exactly here. It's fine because for superconductivity, it is preferred to have the Fermi surface like this or like this, not exactly at the Fermi level.
So one thing which is half possible, mostly these are magnetic systems.
Yes.
And it's like then how you superconductivity sustain.
So there's so it is possible to yes. So I think in some materials you will have found mostly you are right, that's a magnetic material. Most of the times you will find some antiparamagnetic state or like this. But recent experiment shows that it can show some of the materials can show the superconducting state when it is in the topological phase. So particularly this RPTBI type of materials, where R is the rare earth material.
Are these like are these ferromagnets or antiferromagnets?
Antiferromagnets.
Yeah,
Mostly. Antiferromagnets.
So there are many non-magnetic
Non-magnetic
less than film.
Yes, but mostly this bismuth, uh, white, yttrium. Yeah, these things work.
They're not having any.
Yes, yeah. Yeah. So I think both these are true.
But then the kind of
Also, these terbium-ons, we are also tracking this terbium DDPT, and I think that is antiferromagnetic.
then there are many technological insulators. So there's yeah.
Okay, I see.
But I don't know whether you need the surface.
We need here the semi-metal. We need the semi-metal. Yes. So insulator will not work.
Yeah, but as you were telling that band inversion should be slightly away from the Fermi. When you have a
No. Yeah, the point is that once we have this band inversion, this band gets inverted. It's like this one. So in topological insulator, what we find is that these bands are gapped. But here we have to have we need the semi-metal. So here only those things, those situations or those materials will work, which can show this semi-metallicness. So insulator phase will not work.
yeah, these are complicated systems, like multi-orbital systems.
Multi-orbital systems, yeah. And also, actually, there is a recently general theory called Fermi surface. So one condition is that you have to have some this multi-orbital system. That is effective for this Fermi surface. The single orbital case will not. Okay.
Yeah,
Then-
please. Sorry for interrupting you.
No, it's fine, fine. Please feel free to stop me anywhere. Yeah. So this is exotic superconductivity, and I just mentioned that. So it's possible to find exotic pairing. So what are the possible Cooper pairs that I will be talking about? So if I go back to the previous slide, so here we can say that okay, Vogel Fermi surface is possible to find in some exotic superconductor. So now that is why actually I will try to connect. So there might be some ample number of exotic Cooper pairs in those exotic superconductors, and at the same time we can also have the Bogoliubov Fermi surface. So at the connected, this is the question that I will address here. And what are the possible exotic pairs that will also I address. Another motivation behind finding this connection is like that. So in Bogoliubov Fermi surface or the superconductors which host the Bogoliubov Fermi surface, they show the zero energy density of states, and that is always associated with this Bogoliubov Fermi surface. Now, previously in the literature we have seen that it's possible to find the zero energy density of state when the same superconductor hosts a frequency type of plane. So that is the motivation. We are also asking this question: is there any connection between Bogoliubov Fermi surface and off-frequency pairing? Because this is also an exotic type of exotic pairing. It's a different from what the pairing we can find in ordinary BCS superconductors. So I will try to find the connection here. Okay, so then I need to define our frequency pairing at first. So till now I have talked about the Bogoliubov Fermi surface, where we can find and how to detect and how to define that. And then I will go to the definition of our frequency pairing. Mostly now I will take the example of spin-half systems. So that is the case of ordinary BCS superconductors. So we know that we can describe the superconductivity in ordinary superconductors using the macroscopic theory given by Bardeen, Cooper, and Schiffer. So that story is something like that. So if we have a lattice structure, so now suppose an electron passes through the lattice, so it can attract the positive ion cores, so that these positive ions get displaced. Now, it's actually lighter than positive this ion cores, so they moves much faster than this one. So in the meantime, actually it gets locally polarized, so it can attract another electron. And this electron and the previous electron, they tied to each other. So they form a bound state, and this we call the Cooper pair. So in but the BCS theory was explained or the total or described in terms of only one type of Cooper pair. There's a spin singlet Cooper pair, but we have one electron is upspin, another electron is downspin. So how to find the possible spin structures? So let us start with the two electron case where the spin quantum numbers are both are half. Now we can find the total spin quantum number is that is related or restricted by this relation. Now how to represent the Cooper pair state? We can write the S, that is the S spin quantum number, and also the MS, that is azimuthal spin quantum number. Now what are the possible combinations? We can have either S equal to 0 because half minus half it will be 0, and then one S is 0, MS has to be 0. So we can have the 0 0 state. And that we can describe in terms of half and half, that is up and minus up, down, down, up. So that is a possible spin state. That is a spin singlet state. It's possible to find three other states. Those are called spin triplet states. So one S is half, then there are three possible values for MS, that is 1, 0, and minus 1. So these 1, 1 and 1 minus 1, those are called equal spin structure. They will be either up, up or down, down. But here you will have is up, down plus down, up. So this is the mixed spin triplet. So these are the possible spin structure for a when both the electrons have the spin quantum number half. Only is finite. Now, the symmetry defines the properties of an order state, and there is no exception for superconductor. And for superconductor, it is the symmetry of the Cooper pair that describes the superconductivity, and two electrons pairs together here. Now, there is another interesting thing is that if we exchange the electrons of the or particularly if we think about we are exchanging the spins. Suppose we exchange the spins here. So half to minus half, and then again minus half to half. So if we exchange half and minus half, that will give us a minus sign. Similarly, if we do the same spin exchange operation here, we will come out with a plus sign. So these we call odd state with respect to the interchange of spins of the two electrons, and these we call even state. So these are the spin singlet odd state, and this is the spin triplet, it's the even state. Now there can be parity symmetry too at the same time. We can have either S wave, D wave, P wave, or this kind of things. And for parity, so we can have either even parity. Yeah. So we can have either even parity or odd parity. Now we need to combine them, both spin and parity. So now you might be thinking that, okay, all possible values are now we can have several possible combinations, but there is a constraint. So we have to follow the Fermi-Dirac statistics, because when we interchange the two electrons, it has to, suppose we define some pair correlation function. So this is a pair correlation function. I'm not going into the details of pair correlation function, but just you can assume that this F defines the Cooper pair, and then alpha and beta are the spin indices, and R1, R2 the positions of the two electrons, and T1 and T2 are the time parameters. These are time ordering operator, and the psi and psi alpha and psi beta corresponds to the to different electrons. Now it's a pair correlation function. Now if we exchange the two electrons, so that means the spin indices will be exchanged and also the positions. So R1 will go to R2, and similarly alpha and beta. So then we have to have here, we have to get a minus sign here because of the antisymmetric condition. Now following this antisymmetric condition, now we can find out what are possible combinations. So we can have this singlet odd with the S wave or D wave, that means the parity should be even always. Or we can have the triplet state with the P wave, that is odd. So odd even and odd even odd. So even or odd are not possible. Now those are the pre-existing Cooper pairs, where like this spin singlet even parity that can be found in PCS or triplet. Our spin triplet dot parity can be found in UPT3 strontium triplet, but there is some controversy. There are some controversies in strontium triplet. So maybe we can ignore this example. But till now, I have not talked about anything about this time parameters. Here I have just shown that we are exchanging the two electrons basically at the same time. That's why I ignored the time parameter here. In BCS theory also, we ignore the time parameter while describing the properties of any ordinary superconductors. Now, another thing is that there can be some orbital. It can be multi-orbital superconductors. So, with respect to the change of the orbital, suppose the electron 1 is in the orbital 1 and the electron 2 is in the orbital 2. Now, we exchange the electrons, then we need to consider whether we are exchanging the orbitals or not. So, depending on the exchange of orbital indices, it can be again even or odd. Now, there is a time parameter. Now there is a retardation effect. So one electron is coming, is actually attracting the lattice positive ion force, and then after some time another electron is coming. So there are time parameters, of course, T1 and say T2. And this is we ignore, we considered it at the same time, but we can consider this T1 and T2, there is a time. Now, if we exchange the times of the two electrons, so that the same pair correlation function can be even or odd with respect to the change of time parameters of the two electrons. Now, exchange of the two electrons for different times. So, when we including the time again, we should follow the antisymmetry condition. So that results from the fermionic behavior of the electrons actually. So maintaining the antisymmetric condition, now we are actually selecting only the those things which are even or odd with respect to the change of the times only. Now, when we exchange the time parameters of this T1 and T2 only, we are not exchanging anything else. So then we can get either plus or minus. If we get the even state with respect to the change of the time of the two electrons, then we'll call it an even in time, equivalently even in frequency. Or we can get the odd state, that means odd in time or odd in frequency. Yes.
Maybe wrong, but isn't the calculation sometimes?
Yes. Yes, actually delta T matters.
So we will exchange time period the same.
Yeah,
It's just
delta
depend on
T
the
might be
difference.
then minus delta T.
But if you're talking about correlations, what we are
Yeah, that sense we are also right, but we are actually I'm trying to define in terms of this like interchanging the time parameters of these two. Yes, you are right because basically we will go to the Matsubara description. This is basically Matsubara frequency, and once we go there, then it's not equivalent that we are saying. So if you take this delta t and then we exchange it, basically we do it in Matsubara description. So delta t is just reversing minus delta t will that give a difference there, but not if you look at only this. Okay, so yeah, so we are actually defining those odd frequency states from there. Yeah. So now I'm just summarizing what I have told you now. So at first we need to consider the spin states. It might be odd or even state, as I've shown this spin singlet or spin triplet state. Then parity it can be even or odd. So then, if we consider this orbital, then again it can be even or odd. So suppose I'm considering all time orbital and the time or frequency, they are even. Then another possibility comes, then this orbital, with respect to the change of the orbitals, it will be odd. Then we have to flip these things. Now all these four possible paired symmetries are they are even in time. Now the similar counterpart we can have for odd frequency pairings. Then we need to actually take the other possible combination. So what we need to take care that this product should be always odd. So odd multiplies by this even and then odd, it will give us odd, and again even odd, it will again give us odd. So in this way, the product should be always odd. So these are the possible 8 symmetries we can have. These are the maximum possible symmetries. This we can also find is possible to in BCA superconductors, actually we have only found this spin singlet is the first one only. And in other superconductors, we can also find these spin triplet states, but mostly many of them we have not found, but some of them we have found in different superconducting junctions too. So this classification we call it SPOT equals to -1 classification. S for spin, P for parity, O for orbital, and T for parity. And following this classification, it is possible to find the 8 different symmetries. Now, I have defined odd frequency pairings for the spin half. Now, how to define and how to find odd frequency pairing when we have the J equals to 3/2. Now, I have mentioned that I am only considering this half user type of materials when we have the strong spin orbit coupling. Now, strong spin orbit coupling means the spin and the orbital quantum number. So they are not both quantum number attached because spin and orbital they are not coupled to each other. So all the pre-existing classification for spin half system, that is SPOT equals to -1, that does not hold for spin 3/2 systems. Now we actually introduced a new classification which is called which we call JPT equals to -1 classification, where J is the total angular momentum quantum number, P is parity, and T is the time. These are basically operators. So we have written it in short. And now it's possible to find some new exotic pair symmetries which are different from what we have discussed till now. Now we need to check actually what are the possible Cooper symmetries, and then I will identify the which are of frequency pairings. Now we can have two electrons in the same Cooper pair. Now where S quantum, there's a spin quantum number is always half, and then L is 1. So the total J quantum number is 3/2. Now both the electrons have the same structures. Now how to find when the two electrons form the bound state to form the Cooper pair? Now the possible total angular momentum quantum number J that we can find following this relation. Similarly, for the secondary total angular momentum quantum number M that we can find following this relation. So let us have a look at the possible spin states or the Cooper pair states. So we will represent it by just J and M. Okay. So the J, the first possible value is this 3/2 minus 3/2 is 0. So once J is 0, the only possible combination for M is 0. So we can have the 0, 0 states. Very similar to what we have found in spin systems. The 0, 0 state we also have there. Now it's possible to find three triplet states. So 1, -1, 1, 0, and 1, 1. We also have seen that in spin half systems, it's possible to find this three triplet states. In addition to this singlet and triplet states, interestingly, we can find some 5 new quintet states and 7 septet states. Quintet states, that means the J is 2 and M can run from -2 to +2. Similarly, for septet state, J is 3. We can have the combinations like 3 3, 3 2 in this way until 3. Now, how to write down in terms of say half of spin, or so how to write, explain it or describe it. So in order to find the possible combination, so we need to actually use the addition of angular momentum. So we have to find this Clebsch-Gordan coefficient. So finally, I am writing these states of this. I will express this J in terms of this J1, J2, M1, M2. Now, since J1 equal to J2 equals to 3/2, so I will skip this notation. I will only show in terms of M1 and M2. Okay, so now these are the spin structures. We need to consider the other degrees of freedom like orbitals, and we have some suborbits or these kind of things. So what are the possible frequency pairings? I will find out from there. Okay, so at first we need to now describe this pair correlation function again. Previously I have shown that this is F and these are the two position coordinates and the time parameters for the two electrons. And here we had the spin indices like up and down. I denoted it by this alpha and beta. Now here we are introducing M1 and M2 because it is sufficient to take only M1 and M2. So we can ignore this J1 and J2. Okay, now we introduce a new operator for the secondary, which actually which can exchange this M1 and M2. So once we operate the J over F, that will give us this Fm to M1 state. Now again, under this exchange operation, it can be even or it can be odd. If it is even, then we call it a even under the exchange of secondary total angular momentum quantum, or similarly for the odd state. So either even or odd state. So angular momentum, with respect to the angular momentum operation, we can have some even or odd. Now we can take care of the parity because we can define the parity operator, and that can exchange only R1 and R2. Then it can give us again plus or minus. So basically what we are doing, we are defining different operators, and then with respect to the exchange of that operation, we are defining that whether it's even or odd. Now finally we need to combine all of them. So after this, now there is no need to consider the orbital one. Previously we considered S, P, O, T. Now S and O are coupled. So that is replaced by this angular momentum operator. So we have then parity and the time. So these are the individual operations for these are the operations for the individual operators. Now finally when we are combining, again we need to follow the antisymmetry conditions because that comes from the fermionic behavior of electrons, and that is true for in any case. So when we operate J, P, and T, all of them on F, that will actually exchange the two electrons. So following the antisymmetry condition, we will end up with this -1. This is the thing that we are writing in short, that is JPT equals to -1 classification. And that is universal. And that does not depend on what kind of superconductors that we are talking about. As soon as we have some Fermi surface that encodes two electrons, with both of them having this J equals to 3/2, this classification is true. So there are possible now 32 possible states. Previously we had 8 states. Now for spin 3/2 system we can have 32 possible states. I'm just summarizing, so I will not describe in much more detail, then it will be boring. So I will just show one example. I think this spin singlet state J equals to 0 and J equals to 0. Now we can write it in terms of M on A into in this way. So how to visualize this? So previously we had only one Cooper pair, one up electron and one down electron. But now it's possible to have two different Cooper pairs. The first Cooper pair is coming from this two. So 3/2 and -3/2. So this is the possible Cooper pair. And again we can have half and -half. This is the possibility. But the whole state is a combination of two Cooper pairs. But previously we had only one Cooper pair is sufficient to describe a single state. But now for the same single state we need two Cooper pairs. And actually this is a combination of two Cooper pairs. Now we exchange this 3/2 to -3/2. We can also exchange half to -half. Under these operations, so when we are exchanging 3/2 and -3/2, we'll end up with a minus sign here. Now if we exchange half and -half, again we'll end up with a minus sign. Basically, when we operate this J operator on that, we'll end up with a minus sign because it's a additive. This operation is additive. So we have, this is always odd with respect to J. Now we can have the parity even or odd, and again the time can be even or odd. Following the antisymmetric condition, so these are the possible two, either odd, even, or odd, odd. So this is the spin singlet state. Similarly, we can also find the triplet state. So I'm not going into the details. Just want to highlight one point that, so this triplet states, they are something looks like this. So up, this is a particular Cooper pair, and this is also another Cooper pair which can have this 3/2 and half or -half, that you say. And all these are even with respect to J, and then we can find out what are the possible odd frequency pairing. So the odd frequency pairings are even in J, even in parity, and odd in time of frequency. So 50% of them are odd in frequency. And then similarly, we can do the same thing for quintet and septet states. So again, I'm not going into the details. So these are the 5 possible quintet states, and we can write it in detail. And if you are interested, you can have a look at our paper because we have given the whole table in our paper. So these are the 7 septet states, and now we have found, we have identified all the frequency states. This is a summary of the whole table. So we have the singlet, and then odd, odd parity, and then odd in frequency. And also we can find the similar odd frequency triplet state, odd frequency quintette state, and odd frequency septet states. So now we know all the spin structures, and we know what are the possible odd frequency pairings there. And now I will show the connection between the odd frequency pairing in J equals to 3/2 to Bogoliubov-Fermi surface. And already I mentioned the motivation, because this odd frequency pairing can show the zero energy finite zero energy density of state. And similarly for the Bogoliubov-Fermi surface, we can also have the same. So that's why we're asking these questions, that are they related. So what we do, we start from a generic Hamiltonian that can is a cubic material, and that can describe or that can take care of the strong spin orbit coupling. This is the kinetic energy part, and this takes care of this spin orbit interaction, and this is a chemical potential term. Yeah. So the band dispersion will look like this one. So I'm not describing each and every term. So I'm just trying to mention the summary of the slide. So what we are trying to find it out here. So what are the possible conditions? So when we can have both a frequency pair amplitude and Bogoliubov-Fermi surface. And we have explicitly shown in our paper that I'm avoiding all the analytical calculations here. So the condition is that this is the pair correlation function. This is the superconducting pair correlation delta. If its time universe product, if it is non-zero, so delta delta dagger and delta delta dagger minus delta delta t dagger, if it is non-zero, and if the commutator, this Hamiltonian, this is the normal state Hamiltonian, and then we are taking the commutator with the superconducting pair correlation. If this commutator is not zero, if both the conditions are satisfied, then that superconductor can host both Bogoliubov-Fermi surface and odd frequency pair. So that we have shown in our paper explicitly. So, but for the so I'm just trying to avoid the analytical calculation or discussing the analytical calculation here. The summary is that this is the condition to find a particular superconductor which can host both of them. Now, in order to find the relation in a more detail.
Sorry. What exactly is the first one?
So this is a normal metal Hamiltonian. There is no superconducting power. So we need
The
to
only thing J is
spin 3/2 operator. So these are the J is spin 3/2. It's a 4/2.
sort of exchange kind of.
It's a basis, because in spin half we have this half and minus half. Now we need to take care of 3/2 half, minus 3/2.
No, that's true. So
Yeah.
it's a sort of effective scheme.
Effectively, yeah, right.
Effective scheme, yes. So, and then where the superconductivity is coming from?
No, after that we need to construct the whole Hamiltonian, but we write this the diagonal term are normal metal Hamiltonian, then off diagonal terms are superconducting. We can write this Bogoliubov Hamiltonian. Yeah, so here I have not shown the whole Hamiltonian. So what I'm saying that this is a normal state Hamiltonian. Now we know this H naught. Now we need to combine with certain delta to form the total Hamiltonian. Now when these conditions satisfied, then that total Hamiltonian will give rise to both odd frequency and Bogoliubov. So that is the point. Now to have a look at the connection between this Bogoliubov-Fermi surface with the frequency pair in more detail. So what we do that we have some band structures, as I mentioned in the previous slide, but we consider only that band which is very near to Fermi surface. So, and that means we are taking the projection in that. On that we are defining as the band model. Now, when we are defining the band model, so we are ending up with a particular term which is defined by H, denoted by H. This we call this pseudo-magnetic field. This is not the real magnetic field. It is very similar to a magnetic field because this inflates the line node into the finite width region. This gives us the Bogoliubov-Fermi surface. It is directly proportional to the width of the Bogoliubov-Fermi surface. So, explain the role in inducing Gluba-Fermi surface. Now, we have also shown that in our paper, we have explicitly shown that we can also calculate the frequency pair amplitude for the same monohamiltonian, and we have found that this pair amplitude only for Gluba-Fermi, only for frequency pair amplitude state, that is also directly proportional to this H term. So if we tune this H, we actually cannot externally tune H. But the point is that if we manually just tune H, that will control both the Gluba-Fermi surface and our frequency pair. So this is the H which is connecting both. So that we have shown explicitly in our paper. So thus this pseudomagnetic field, and it has no other physical explanation. Is only just like a pseudomagnetic field. It is directly proportional to both Gluba-Fermi surface and on frequency pair amplitude, making the connection between the levels.
So where is this edge coming in the Hamiltonian first?
Sorry, I didn't get you.
So how is this edge coming into the Hamiltonian in the first place?
Oh, okay. Now, if you look at this H, it's actually taking care of particular component of this delta, that means superconducting delta pair correlation. And then we have some sort of normal state contribution too. Is actually combining some normal part to some superconducting correlation. So apart from that, we actually do not have any other explanation.
And what is epsilon prime in now?
This epsilon prime, I have taken. Yes, this is epsilon. It's a very similar to a normalization factor. You can think about the normalization.
So what is the origin of your pseudomagnetic field? Is it strange?
No, there is no physical explanation for that. Not straight. There is no straight. There is no straight.
So it's basically what you have to Hamiltonian and then map it to the Hamiltonian on the scale. And then you can map it at whatever the function you have. Map it towards
Yeah, we are taking the projection, but even if we ignore taking the projection, if we consider the full Hamiltonian, in that case too, we will end up with this kind of figure.
Since you said these system, I mean this could be found in topological insulators.
Not topological insulator.
Not in topological. Or, I mean sorry, topological semi-metals.
Yes.
So is it possible that this pseudomagnetic field could be related to the
Pseudomagnetic field, yeah, it's a good question. I have not thought about it, might be. Because in any way, those things are, yeah, it is topologically protected.
yeah, and that
So
also
that
acts
might
like
be
a
related. Might be related.
always be like that.
Yes, yes, so it should be.
But here, I think mechanism is something like here the epsilon is relative to some energy.
Yes, exactly.
And, but you have E prime, which is derivative of the energy.
No, it's a not
No,
a
it's
derivative.
something
It's
else?
just E prime is just, you can think about like a normalization. Because E1 to E2 before we have all these things here. Yeah, here we have this E1, E2, E3, E4, E5, and then that using that we can define it. Yes, I think there is.
Many questions.
Oh, self energy. No, I think no, because we have not considered any open system here. We do not have any external perturbation, so I think it is not related to self energy. It is completely intrinsic. Yeah, I think there is one more hand raised.
It's the same person.
Is the same question? Oh, okay, okay.
Can ask. That's
Oh,
the same
same.
person.
Yeah. Is it fine? Does this answer your question?
So bunker is, yeah, okay.
Okay, so welcome. So how much time do I have?
5 minutes.
5 minutes. Okay. We will then just
question time.
yeah. I will skip this part mostly, but I just want to show one thing. The thing is that so not only this table I have already shown. So we are taking the okay. At first, this is the total Hamiltonian. Yeah, this is the total Hamiltonian. You are asking this question. The normal part Hamiltonian, and this is the delta that we are taking. Now, I just want to highlight this one point. This table I have already shown. Now, this is not that this is an abstract classification. So we just then try to find those pairings in Hamiltonian using some generic Hamiltonian. We use the same Hamiltonian, and we have shown that it's possible to find different pairings that we are describing in the table. So using different delta. So we have tried with different delta. We started with SX infinite, and then with you have taken this S plus P, and then we also this is the P delta P, and also yeah, and particular this type of pair correlation function, or where we have some sort of S type part and then some sort of this chiral D bit part. When we have this mixture of those the things, both the things, then it is possible to then it's highly possible to get this or different kinds of frequency pairing. That's it. And this particular delta will definitely give us this Gluba Fermi surface, because there are several works which predicted that this delta gives rise to Gluba Fermi surface. We have also taken this example, and we have seen that we are getting all different kinds of possible Kubo pairs which we have classified this before. So I'm just keeping this part full time constraint. Okay, so yeah. So it's possible to find some inflated regions in momentum space, and that is topologically protected Bogoliubov Fermi surface. Now, after that, I have classified all the pair symmetries for spin 3 by 2 systems, and it's possible to find this kind of different Bogoliubov Fermi surface in some exotic superconductors. So then we tried with some exotic superconducting pair symmetries. It's completely different from the conventional BCS pairing, also different from the non-center symmetric type of superconductor. So and finally, if I tried to connect the Bogoliubov Fermi surface to this exotic pairing, particularly frequency pairing. Yeah, so thanks for your kind attention.
So, in the initial stage, you spoke about, okay, firstly, are there any experimental candidates for this? I mean, how do you, relate what you have with those
Experiment candidates for what? This Bogoliubov Fermi surface?
yeah,
Or?
systems, yeah.
Okay, Bogoliubov Fermi surface. There is, I know the some group are there doing this experiment. They're trying to find out. Till now, there is no experimental work reported so far. But there are some reports for this J equals to 3 by 2 superconductors. Particularly, they found some different properties which are different from basic superconductor, and they have shown this superconducting ground state and different possible or signatures of different exotic pairings that they have described in some experiments. But there is no.
Like since I don't come from the field, so what would you see as a signature for a J equals to 3 by 2? Yeah, what would you?
Okay, so J equals to 3 by 2 at first, what if we are looking at the superconducting state, then we have to come back to this exotic pairings. So for spin structures, basically what happens that they get contaminated. So it's extremely hard to find out individually and then find some individual signatures. So in this way, actually, we find out like here what I discussed, that we have this frequency. I just try to identify the odd frequency pairings, but those odd frequency pairings can have different possible spin symmetries. What we can maximum try that we can just try to get a situation where one of them dominates. Okay, then in that case, since we know the some from some previous reports, we know the possible signatures of our frequency pairings. So in this way, we try to map that whether it's possible to find the same signature in these systems too. And we got it. And now, if you ask me to separate one of the odd frequency pairing, probably it's impossible. So we can get maximum the all the possible strings. Then we need to separate the spins at first. Then we need to do some engineering to separate the spin structures. Suppose in spin half systems that I know, I tried in in a different work where we had some this wild material and superconductor junction. So we had some spin polarized surface, and then that we used to separate out this up odd frequency. So in this way, we can maximum separate out one of them and then try to get the signature. So with that. And mostly people have found a different, mostly calculated or also in experiments, the Josephson current. Sometimes there's this band structure calculation, they will also finite region and all those things. And try to look at this superfluid density as at the same time. So whatever the I showed one slide for the detection of Bogoliubov Fermi surface. So some of them are also true for individually for J equals to 3 superconductors.
I know it's general. So, in system where electrons can form singlet,
Yeah.
why is it energetically favorable to form string 3 half?
Okay, yeah, a very good question. Thanks. At first, if I come back, so, you remember that you can go back to that slide. Yes. So in this system, so as soon as we arrive at the situation of band inverted band structure, inverted band structure, here we can have both of them are penal. So that means it's only possible to get J equals to 3 by 2. So it's only possible, we are considering only those materials where the Fermi surface actually encodes the electrons only spin 3 by 2. There is no spin for Fermi surface. So that's why in this material, it's possible to find the superconducting state for J equals to 3. But if we have some other materials where both of them are possible, then of course, yes. Then you
So here, when you are saying that there's a two dot spin,
yes, there is.
right? They are mixed. But generally, in these materials, are very weak spin out.
Yes.
Right? So you want to have 3 by 2. I would expect, maybe what kind of a spin order?
Okay, yeah, that's a. I actually I did not check the exact value of the.
This was the school chances. It's pretty large. It's pretty between 0.8 dB or something. I mean the splitting influence is huge when you have it orbit like you have the effect. I mean, she spoke about all these heavy ones, and if it's P, then it should be large. Even gallium arsenide and all, like,
This much is the largest. This much is what you can
And if you have this weak spin orbit interaction, then it's possible to arrive at that situation that you was talking about. It's possible to have both half and 3 by 2. And then we end up with a half down step with a half.
But effective is still having 3 by 2.
Yes, effectively, yeah, because these are not good quantum numbers in that case. Whenever the spin and orbital are there.
I mean, it's P.
P is what giving you one and less than
Yeah.
half.
But sometimes what we tried was so that we are taking care of the situation where we have this weak spin orbit coupling. we considered, okay, interactive steam hub. Let us consider if we have this hub. Now what we tried, we both this effective steam distributor and hub, we ended up with the same results. So one big, we are checking actually this frequency pair amplitude in that Hamiltonian, and we considered both. So so that's why it's sufficient. It's fine to consider this spin half if we are considering this very weak spin orbital.
There's one online question. One second. Can we get a Sarma phase out of these BFS systems?
This is Shama's.
I don't know.
Do
Do you want to unmute yourself and ask the question?
Can you explain a bit of this Sarma phase?
Oh, okay, this Swarma phase basically comes due to the polarized Fermi systems, polarized superconductor or superfluid Fermi systems. So they are basically the saddle points of the free energy, the thermodynamic potentials. So can we get such
I think
systems?
there is no polarization in that sense. So I think they might not be connected.
Mm.
Yeah, because
But you are telling that there is the zero energy excitations. I mean the Bogoliubov Fermi surface.
At the same time, it is also true. For example, I can comment on this odd frequency pairing. I mentioned that odd frequency pairing can show this zero energy, finite zero energy density of state. But whenever we are getting some finite zero energy density of state, that does not guarantee that it's odd frequency state.
Okay,
So
but
I think the point is that whenever we are getting this some zero energy excitation, the question is valid, of course. Then we need to check. Unless we check, I think we cannot make it sure.
yeah, because for the Swarma case also, Swarma phase also, there we have the same conditions for
Okay, I see.
yeah. So that's why I'm
Okay, sorry, I am not aware of this trauma phase, so that's why maybe I cannot comment. But I have not shown any kind of polarization, so there is no polarization needed for this
okay.
particular case. So
Okay.
if you are talking about the zero energy excitations, then one need to check whether there is
Yeah.
any connection.
Yeah, there might some have some connections.
Okay, I see. Yeah, then one need to check. Yeah.
Thank you.
Thank you.
Yeah,
Okay,
thanks. Yeah.
Sanjay,
Just have a question regarding how you are deriving that Hamiltonian. So,
Share this band.
so from the normals, do you write a Hubbard model Hamiltonian and
No,
then
no,
do a
there is no
mean
Hubbard
calculation?
interaction. Okay, I can go back to that structure.
How do you generate that delta? So you are
No, we are not actually we are not generating. So what we are constructing a Hamiltonian. So let me go back to the slide. Yes. So this is the total Hamiltonian. So we are writing this Hamiltonian in number basis. Okay? We have both the electron and hole part. So this H naught is the normal state Hamiltonian. This is the counterpart, the whole other whole part. This is electronic part and the whole part. And this delta, this is since we are doing the model for model calculation, then this is the superconducting delta. So that is responsible for superconducting. And we have considered different combination. Suppose if someone considers only we can consider this singlet as well, that is suitable for DCS. Then we will replace this delta by that only that expression that I have shown. I think.
so the Hamiltonian that you have written at the top, no, for the previous slide. So
This is the normal
this
state
is the
Hamiltonian.
normal Hamiltonian
Only
with the
normal.
spin orbit part.
Yes, we have the kinetic energy part and spin orbital part and then
chemical
chemical
potential.
potential.
Then you do a BTG transformation
Yes.
and arrive at this HK.
Yes. Yes. But is this H naught will just replace by this.
Yeah, that I understand. I'm just
Now delta.
delta. How is it really?
Now if we consider this S wave pair potential, we are doing different models. Okay? We are considering different models. Now if we consider there is only S wave pair potential, then we will replace this delta K by this term. This delta S is nothing but a constant term because it's independent of K. For BCS, the delta is independent of K. And since it's a 3 by 2, we have this 4 by 4 spin structure. So now we need to sum this kind of unitary operator. Now, if I, instead of S wave, if I consider suppose S plus P, then for the P part, this wave potential looks like this. It's a more complicated structure, and it depends on K. It's a momentum dependent. Now, if I go to the D wave, we can also consider the D wave. So here we have actual mixing. We have some sort of S wave part and some D wave part. Then D wave part is again momentum dependent, and this part is not momentum dependent. Then we will replace that delta K by this expression. So we have tried different models with different delta K.
So how is that spin orbit part, the kinetic energy part directly comes down and gets replaced by the H0?
Yeah, in H now we have both kinetic energy, spin orbit, and delta. So whenever we are replacing this H now, that we have all the terms in the whole monitor.
Okay, so if there are no other questions, then let's thank Paramita for a nice talk. Obviously, I can do it also.
Yeah, you want.
Just why this you?